Yeah, everything looks good. So, yeah, hi everyone, whoever watching this video. Today I will be presenting my presentation on the course Cox 510. This is a course at University of Arizona, and Cox 510 course is computing for neuroimaging, and for the course project I will be focusing on how do you visualize diffusion tensor imaging images from like using this software DiPy, and how can you uh, kind of merge DiPy and Surf Ice to create some amazing visualizations for the DTI data. So let's get started. So here's some introduction. So what's DTI? DTI is an imaging technique which kind of tells the structural connectivity of our brain. It can tell like how the white matter is connecting regions of the brain and how the communication is happening in terms of structure, and the modality it measures is the direction and magnitude of water molecule diffusion. And after generating the data, there's like a lot of processing is done, kind of generating a lot of tractography which tells like what are the white matter pathways, and here's like a color encoding scheme which is used to represent the direction of the white matter tracts. So going to fiber tracking, what's fiber tracking? Fiber tracking is, excuse me, a process of reconstructing the white matter pathways from the imaging data, and this is done by creating streamlines from the directional information. So we get this directional information from the DTI images, like, okay, which direction the water molecules are diffusing, and it kind of tells the direction of the white matter tracts, whether it's going like left to right or right to left or up down. And I think in it's bi-directional, like cannot not sure if you can tell like which direction it's going on, so it's considered like bi-directional. And coming to tractography estimates the path of those white matter tracks, and using tractography we can do some visualizations to study the brain connectivity. And so usually the fiber tracking usually involves 4 steps. uh, so the first step is about the method of getting directions from a diffusion MRI dataset, and the second one is, so the first one is like how do you even start the tracking, and like in which direction you want to go for the tracking. The second one is, okay, you've started the tracking, then how do you stop the tracking? Like what are some of the thresholdings or some kind of like parameters which then if you touch them, they or the algorithm when reaches them, those parameters, then the tracking should be stopped. And the third one is a set of seeds, like, okay, which I think this is about like which part or like which direction you want to begin the tracking with. And this final one is selection of tractography algorithms. So we'll talk about the algorithms in like the upcoming slides. And the basic behind tractography is that given the local directionality of a tractor pathway, you can integrate along like do on the segment to build a complete representation. So you can start from like one point and try to calculate, like put like the directional tensors in one over the other, which kinds of like you can recreate or reconstruct the whole directionality from one point to another. Yeah, so like I was saying, there are basically 2 types of tractography. The first one is deterministic, where uh, so according to the definition, it's like it can be viewed as a maximum likelihood estimation of the fiber trajectories. So wherever the direction it finds the maximum of the tensor, it goes in that direction and kind of try like do the reconstruction of the fiber pathways. The other one is probabilistic, and when the tracking started, it samples the tracking direction from a distribution. And I would say, like, in my opinion, there's no like one method better over the other. It's just about like, I would say it's more of a case to case basis, like which tractography method you wanna go with. And there's another tractography method, EUDX, it's called. So we'll get to know about it in further slides. Like it is one of the tractography methods available in the DiPy program or software. So after, so we got some introduction. Now we want to see what is DiPy. So DiPy stands for Diffusion Imaging in Python, and DiPy is built on top of the Python scientific stack, which includes NumPy, which is numerical Python, SciPy is the scientific Python, and the very common plotting library, the Matplotlib. And DiPy is, I would say, in my experience, is like a full-fledged software of working with diffusion imaging in Python, which contains like a lot of pre-processing tools such as motion and eddy correction, because since DTI images are prone to a lot of noise, so these are some of the pre-processing steps the users perform before going into analysis. And as I mentioned previously, DiPy also has a lot of deterministic and probabilistic fiber tracking algorithms and some newer algorithms like constraint spherical deconvolution and the diffusion spectrum imaging. And so this was all about the processing, but what after processing? So DiPy also has a lot of visualization tools, which we'll look in the tutorial, like how can you visualize a tract and can export to different formats such as PNG, SVG, and or you can export even like the whole tractography algorithm. So using the algorithm, you can export the tractography in a TRK format, and then you can utilize some other tools to visualize it if you don't want to use DiPy for visualization. So for this tutorial, I've summarized the methods we're going to look at here. So the first one is like DiPy installation, and then there will be like basic tracking. So we'll go through these three algorithms, and we'll go through how do you go about generating the connectivity matrix at the end with all the three cases. So, and this is mostly the tutorial part where we'll be seeing the commands and uh, the the packages, the functions which we'll use. And the next part is visualization, where we'll see, okay, how can you use tractography with DiPy, and then tractography with Surf Ice, which is another visualization software, and then how do you visualize the network connectivity with Surf Ice software. So before going to results, so yeah, so we'll talk about these results, but I would like to just stay here for some time on this slide and go through the uh, code first. So and I'll say that uh, I put all the code on my GitHub. So and then so yeah, here's my GitHub. Like I'll so yeah, I'll put the link in the I've put the link in somewhere in one of the slides at the bottom, slides at the end, and then we'll go through all the GitHub notebooks here. But first, just to start, so uh, you can use like pip or conda to install. So okay, let's talk about installation first. So you can use conda and pip to install DiPy. I would say what I did is just to make a new conda environment so that I don't disturb my other environments, and just start with a fresh environment and install it. So let me open. Yeah, so if you go to tutorials and then quick start, then it can just like, so does it have, oh, give me one sec. I don't think, yeah, so here, yeah, so either you can do like pip install or conda, and then DiPy is available for like all the main operating systems like Windows, Mac, and Linux. So I'm running a Linux machine, so I use the Linux version of it. Yeah, like this, Python and DiPy, and then I'd say like, yeah, so for visualization we need this Fury library, so it's a good idea to just like install both of them together, and then also to visualize the reading, visualize. So for visualization we first need to read it. So for the nifty images we need to install the ni babel library. Yeah, so this is all about installation. Then what you do. So DiPy has like a lot of uh, data sets. So you can just run the commands and then it will fetch the sample data set to your PC. So let's go here. Uh, can you just give me one sec? Yeah, here I think so. This is all about like just collection of all the functions we will be using in the first code, yeah, in the code I would say the cell. And then so there's like something different I'm doing right now is that instead of using a command for fetching the nifty images, I've already downloaded them. It's the Stanford Hardy database, with these images, which has like one sample DTI image. So I've already downloaded it, and then you can see like there's like a folder here. It's called Stanford Hardy, which contains all the files. And then I just know the path, and then I call these paths in the functions. And these are the functions like load nifty and then load nifty data, which is used for loading the nifty data, like the nifty images, the nifty images which contains the DTI in values. Yeah, and next we need two things. This is the bval and the bvec information about the magnetic field used for DTI. So we have these here, and then you can just like use and define like, okay, what, so I would like to mention that with this data we get this label info images, which uses like one atlas and has like uh labeled some of the brain regions as some numbers. So if you can see here is all of these, 1 and 2 is mostly the white matter tract and around corpus callosum, where all the connectivity between the left and right hemispheres happen. So, and then other brain regions have like some numbers associated with them, like you can see like thalamus or hippocampus, and the other the frontal cortex, the lateral orbitofrontal cortex, and and the temporal lobes. So each and every region has like some number associated with it, so that if you want to look at like what kind of white matter connectivity is there, you can mention these label into the algorithm, and then you can extract them. So for this tutorial, we'll just look at the basic connection around the corpus callosum in the central uh, part of the brain. Yeah, so after loading the images, we would like to visualize like how do they look. So this is just like the axial middle region of the brain, which you can see here is all the DTI images in the Nifty format. So what we are doing, just loading the Nifty, then extracting the volumetric data and kind of visualizing it in this command. And then you can load the uh, the gradient of the magnetic field in using this gradient table format command. And then, and like I was discussing, we have like the labels given with each and other brain region. So 0 is like the background, uh, and then the other different regions are given from like 1 to 88. And then, so for white matter, we'll say either so this binary dilation, which is used to kind of like say that, so white matter array just tells that, okay, if take all those regions which are labeled 1 and 2, which contains white matter, and then rest put 0 to rest of them, which becomes like our other brain regions, other than the white matter regions in surrounding corpuscallosum and some part of the cortex. and and this is the tractography function, like peaks from model, which kind of run the tracking. And then if you visualize the sum of the peak track direction, so if I run this command, then you'll see like like one of the window pops up. uh it might take some time. Let me see how much time it takes. Yes, a window pops up, but I'm not sure if you can see this. So let me uh yeah, so let me change to that. uh how do I change it? Yeah, I'm just trying to figure out like how do I change. Let me just stop share for a while. Yeah, and then I'll just share my screen again. And mm, yeah, so I think if I share like all the desktop together, then I think you should be able to see. So this is like the basic tracking we done, and then we found like some tracking information. So we got like one slice of the brain, and then we can like visualize how the white matter connectivity is arranged. So this is like the one part kind of visualization you can do in DiPy. Like you can just like zoom in and it can tell you the direction, or and then like you can see like here's some like it's green and then red and the blue. So like it's like from like top to bottom or left and right or front and back. So and then you can find like some of the diagonals are like multicolored. So like for example, if I zoom in here, you can see like these uh violet uh colored, so which kind of tell that okay, two directions. It's kind of like on a diagonal of merging between the two axes. Yeah, so this is like one kind of visualization you can do. Just see it like nicely. Yes, I'll stop share and go back to my Jupyter notebook. Uh, so let me go back to my Jupyter notebook now. Yes, so we are back to my Jupyter notebook, and after that, what you can do is like tell. So this was just like basic track. Now we haven't started tractography yet. We just saw the direction of the fibers. So, and then we have to mention these threshold stopping criterion, like where to stop. You can mention the stopping criterion with using this command, like threshold stopping criterion here. And again, we can use the local tracking function to so now start the tractography here. And this takes like a lot of time, like 5 to 10 minutes to run on my machine, but I've already ran it, so don't have to really worry about it. And but for the first time, if you'll run it, might take some time. So we'll see, just visualize it, like how does the tractography even look here. So if I run this command here, it might again take some time to load it into the visualization box, and uh, then again I'll stop share and then start share the whole desktop. So yeah, now you can see there's like one small window which has popped up here, which has the tractography information. And then this is kind of tells like the tractography of like white matter fibers. Here you can just like roll. So it's like, so this is like the left part here, and then this is like the frontal cortex. It's kind of, yeah, and then this is like the back, like the posterior region of the brain. Now we'll go to the like the superior, like the upper region of the brain. So yeah, like you can just scroll or just play around, zoom in, like explore, like how, yeah, this is so like, yeah, in terms of like visualization, this is a very nice tool. I think it usually utilizes the VTK tool, which is like embedded into DiPy, and then you can visualize it. Yeah, so like I did the same analysis for with with all the three tractography algorithms like EUDX, and the EUDX is Euler delta crossings, and the deterministic algorithm and the probabilistic algorithm. So I'll stop share again and then close this VTK, and then again let me go back to the Jupyter notebook. Yeah, here. Yeah, so after generating the tractogram, you can just use this save trk command to save the tractograms. So, and why we are doing this, because we would like to visualize it into the Surf Ice software later. Yeah, so if we go to now go to the connectivity part, but we can see is like the steps are again the same. So I initially like there was like two different tutorials, like generating tractograms and then connectivity. So I've kind of merged both of the tutorials together and then repeated the same analysis for the all the three algorithms, so that starting from the DTI image till we calculate the connectivity matrix is like end-to-end tutorial for all the three algorithms. So that's like one of the objective behind this joint tutorial for the all three algorithms. So I run the tractography again here, and then after running the tractography, what you can also visualize is that you can have the nifty image, visualize a nifty image along with the tractography, and it might tell you more about the connectivity. So this code, if you run this code, you'll see, yeah, in a few minutes, I suppose. Uh, yeah, so it has opened. I'll just stop share and then share again. Next up, yeah. So now again we have like a small box opened, and then we have, and we like this. So this is like the kind of merging between the Nifty and the DTI fiber tractogram. You can see like if I just like rotate it, you can see, okay, it's like nicely placed. This plane is nicely placed between the mid, and then you can say like this is like the front of the brain, like the anterior, and now we go to the posterior. Now go to the superior part, and then you can say like the Nifty image is like nicely overlaid with the DTI fibers. Yeah, so this is like, so I would say in my opinion, DiPy is like really nice with visualizations. You can just like go in, or just like zoom out, zoom in, rotate. If you want to see specific regions, you can see from here the caproscallosum inside, where's all the left and right connectivity is happening here. Yeah, so yeah, so I'll stop share again. We go back to our Jupyter notebook. Um, yeah, so this was about like visualizing the Nifty and tractography together. Now we can use this connectivity matrix which runs on the streamlines, which is the tractography information which we had obtained from the previous analysis, and we can run the connectivity matrix which will use the streamline information to give us like the uh, 2D heat map of all the connectivity between different brain regions. So if you run, and then this is like the final output I would say we are looking for in terms of the brain connectivity between different regions. So what regions we are talking about? Like I mentioned, this example uses the this atlas which has about like, excuse me, 88 brain regions. So these 88 brain regions are like are the rows and columns, and uh, this 2D heat map tells us about the connectivity. There's more brighter values tells us like the more higher the connectivity is, which is also you can see the diagonal, which is like the connectivity in the same region. Yeah. So again, uh, uh, and then you can like pre-process it or just say that okay, if you're not interested in some regions, you can just zero them out, and then you want to see some of the other regions, so you can see them here. And then since this is like a numpy matrix, you can just save it into, first convert it into a data frame, and then save it as a CSV, because you would like to use this CSV which has the connectivity information to be like overlaid onto the network. So we'll see that how we're going to do it like in the next part of our tutorial. So when we will be using the DiPy, sorry, not DiPy, the Surf Ice software to visualize this connectivity. So similarly, this was EUDX model, and then similarly you can just go to the deterministic one where this remains the same. The only thing is that uh, the the tracking changes. So initially we were just using this some kind of local tracking here, and then now we would be using, oh, where's that? Okay, let's start from the beginning. So we just first load, so this is the deterministic version of the tractography algorithm. Again, we load all the required commands, and then the file paths, again load the nifty, and then also do this, the marking of the white matter tracks like label 1 and 2, level 1 or 2, and rest of the other brain regions would go to 0 while creating this matrix, and then again run the binary tracking. And this is the difference here, is that we are running a deterministic maximum direction getter, which is one of the deterministic tractography algorithms available in DiPy. And then we run the local tracking from here, again generate the streamlines, and then again our final objective is to get to the final connectivity matrix. So similarly, like as uh, as shown in the EUDX part, you can run this in streamlines the tractography visualization, and then again uh, it might take some time to run for the first time. Yeah, it's taking a while. We can wait for like 2 or 3 minutes, I think. Yeah, another thing you can do is just like just save the tractography files, and then you don't have to run it run the Jupyter notebooks again. Just can load the tractography files separately and then visualize them. Yeah, I just hope it opens quickly. Not sure if it's because of my machine is slow or yeah, it just takes some time to open. It's taking too much time. Okay, we can just move to this. Yeah, it just opened. Wait, I'll just stop share and then reshare. So yeah, so similarly for the deterministic one, we have this kind of very nice visualization of the tractography here. And then yeah, I can just like rotate again. Yeah, similar to the EUDX, like the previous algorithm, you can just like zoom in or rotate. Yeah. So yeah, that was the tractography visualization uh, for the deterministic algorithm. Then again, we go back to our Jupyter notebooks and then see again here we can run this connectivity matrix function on the tractography streamlines. We get this kind of like nice connectivity, and I'd say like there's like a difference between the connectivity. I would say just depends on like what kind of algorithm we are using. And again, I would like to mention that I posted this uh, code on my GitHub. So if we just sorry for that. Yeah, if we go to my GitHub, I have all the EUDX model Jupyter notebook and the deterministic and probabilistic. So we looked at EUDX and the deterministic. So we can just try to see this probabilistic uh, tutorials again, like we did in the Jupyter notebooks. Again, load all the libraries and all the functions. I mean, in terms of library, it just uses SciPy and DiPy, so not much. Just and then like Fury and the backend. Then show like look, put all the paths again, load nifty images, put the mask, and then here you can see that like the tractography algorithm is different now. We have using this probabilistic direction getter algorithm on the spherical deconvolution model. And again, if this was like actual Jupyter notebook running, we just use this command to run in the using the Fury package, and it would open a really nice tractography visualization. And then again for connectivity, we say okay, we are interested in the white matter tracks at the label 1 or 2, and then you can end up with this nice looking connectivity matrix. Yeah. So that was about generating the connectivity matrix for all the three different types of. I mean, there are some different algorithms as well, but for just this tutorial, I just focus on the three very common ones. And now we go back to slides. So here, yeah. So we are done with the first part where we just go through the code, and I'll show you some results. But right now we are interested in visualization. So first I'll show you how to do a DiPy and then go with Surf Ice. And the last one would be like visualization of DTI network connectivity with Surf Ice. So for the next slide, I have the superior view of the brain uh, for the three different algorithms, and I'm pretty sure you can see there's like slight difference between the connectivity, or I'd say the tractography, but just because the inherent tractography algorithm is different. So I'm not sure how to quantify this kind of difference, but in terms of like quality or like visualization, you can see like all the three uh, track tractography visualization images are different from each other. And this was just for like the superior view. And in the next slide, I have put like the superior, posterior, and the left view to just kind of illustrate like, okay, different tractography algorithms would give you different kind of views, but I mean, it's up to the user, like which algorithm they think would be best suited for their purpose. And this is just like a comparison of the connectivity matrix between all the three different algorithms we have used. So you can see like this, like some slight difference between the Euler delta algorithm, the deterministic and probabilistic. Like if you can see like some of the regions and in the like some other corners, you would find that there's like some subtle difference between all these three. But I'd say that it's not really clear, like, okay, how this 2D heat map for these three algorithms is different. So for that, we would like to use some different kind of software to just to get a good view of the network connectivity of generated by these three algorithms. So for that, before we go into that, I would like to mention that another analysis which is not mentioned in the DiPy tutorials, which I have put here, is that you can try to see if are there any densely connected regions between in the DTI tract by doing like a clustering analysis. So if you can see like this is the order of the brain region is like is the same as the labels in the label file, like region 1 to region 88, but this clustering analysis is different. It would just cluster the most densely connected regions together. You can find like, okay, so wherever you find like very red colored squares in this image, you can say, okay, these regions are highly connected to each other. So for the Euler delta crossing algorithms, you'll find, okay, there's like one small square in the middle of the image, and then there's like one big in the corner. But for the deterministic tractography algorithms and the probabilistic, you'll find, okay, you have like a little bit of like some squares around like 20 or 30 regions together in the lower bottom corner. But you can see like based on the clustering, it can show this analysis is telling that if you see the upper left corners of these images, there's like a difference in the strong connectivity. So that's kind of like justifies or validates the point, like different tractography algorithms will give you different kinds of connectivity, and then based on that you will get different types of densely connected regions. And so this is just like one example of like how we can use the connectivity information to get more uh, like a more deeper understanding of the connectivity with DTI. And now we go to the other visualization part. So till now we've looked at uh, like how do you even go with visualizing the DTI images and the brain fibers, the white matter, and the brain connectivity in the all regions depending on your brain atlas. But we are missing three things here. The first one is like, so we have linked with brain regions with connectivity, but unless you are like very good at remembering stuff, it's not very sure, okay, which region is like very highlighted. So if you do not know in this image, okay, what was region number 56 or let's say 74, any number between 1 and 88, it's kind of difficult to uh, remember that, okay, these regions are connected. So for the next part, I would like to visualize them more better. Like if we can overlay this connectivity matrix over uh, a network in and then visualize it on a 3D 3D kind of format, then it would be really nice. So that's the next part of this tutorial, that so we'll focus on linking brain regions with connectivity matrix, and then mostly surface based visualizations. And then since this is like an 88 by 88 connectivity matrix, you'll find that it's like 88 squared is the theoretical number of edges we can have. But what to do if you're not interested in like all the edges, but just the highly, like the densely connected regions? Then what we can do here, so the idea is that you can use the Surf Ice software to kind of overlay. So uh, I'll start with the basics first. So the first idea is that we have to convert the volume based atlas to a surface based atlas. And I have the regions, like I'll show you like why this is important in the next slide. So, and then another important thing, I would say the most important thing to visualize this is to convert the surface space atlas into the network nodes. So I've used this SPM package to kinds of convert these brain regions into, so like I said, this tutorial uses some atlas which has 88 brain regions. So we get like this 3D network of 88 nodes, which kinds of locates like the central part of each region. And then we can overlay our connectivity matrix over these nodes to kind of visualize it. So this was so before going to the connectivity matrix, this is just an example of like how do you visualize white matter tracks in Surf Ice. So I'll give you example for each of the Euler delta, deterministic, and probabilistic tractography algorithms in just a second. So if I stop share, and then I'll show you like how do I do that. So let me share the Surf Ice software. So this is the Surf Ice software, and then if you wanna go load, first load some of the atlas. So like for some of my other projects, I've used the AL3, the anatomical labeling atlas, which is like the most recent ones. But since this Stanford Hardy database uses the APARC reduced, uh, so I'll use this and kind of overlay the tractography. So if I open this here, so yeah, if I open this here, so we get like a nice region. I can just zoom in here. Yeah, and then you can just like rotate, and then you have like different brain regions. And then another thing, so if you're thinking that okay, this is just showing the surface here, there are options here, like if you can just clip the like some of the brain regions in like this part, or you can just like change the plane and then again clip it like this. And if I go and overlay like one of the tracks, so this option of like add tract on it, let's say add tract. And if I like, for example, if I want to overlay the per. Yeah, so I'm back again because my Zoom died midway. So we'll resume our tutorial. So let's go and see. We were here, and I was trying to show you how to do. Let me go to slideshow. Yeah. So it's trying to show you like how do you use Surf Ice to the track visualization. And then I think if I just stop share and then again go to Surf Ice. And yes, so here we have loaded the probabilistic tractogram over the brain atlas, and you can just see like, okay, this is, and now it has like become heavy because the tractogram is just like a very heavy file to visualize here. Yep. And what you can do is I think you can just can go here and then just like save the images or open something. I mean, you can just do like a lot of stuff here. And yeah, so that was tractography visualization, which we got from DiPy and then visualized them into uh, Surf Ice. And then another thing, what you can do is just go to views here and then choose like superior. And now you can do like a lot of things. Either you want to do a render, change to flat render, or just there's like so many options of different kinds of like how do you even view the mesh. So let's say, yeah, and this will use like a lot of processing, I think. Yeah, and then go here and then you can just, if you want to go like go to wireframe, this is like one personal, I like this one. So yeah, and then everything becomes like a wireframe. It will be heavy on the processor. Yeah. So I go and then just close everything down and let's go back to the Jupyter notebook. Where's the Jupyter notebook? Uh, yeah, so we were having this. Yeah, so I was showing you these slides. Yeah, so this, like I said, I uploaded the Jupyter notebook on my GitHub. I'll provide a link below, and then let's go here. Yeah, so this is the track visualization view, and then I showed you a demo of how to do this in Surf Ice. And this is for the probabilistic. We just saw this like a few minutes ago, and now we'll see like how can you do this kind of visualization in Surf Ice, like instead of the tractography visualization, if you want to do the network, like the edges and the nodes and visualize. And that was the whole reason behind doing this surface-based atlas to network nodes extraction, so that you can kind of visualize this. So I'll stop share and then I'll show you again. And yeah, here I would like to mention that if you see the central node, it is the corpus callosum. So which kinds of is the place where all the white matter fibers connect the left part of the brain to the right part of the brain, and then like, and instead of like visualizing all these edges, like we can do the thresholding. Like we just want to see like which are the most highly connected regions, and then if you want to do like a step by step thresholding, we said that in the final image we see that okay, all the highly connected regions of the left and right vein pass through corpus callosum, which is like a very basic fact in neuroscience, that corpus callosum is the place where all the left right connectivity happens, but we can also visualize it through our tractography and this kind of surface visualization. So I'll show you like how to do it. So again, stop share and then go to surface, and for to visualize it here, we just first load, go to open, and then first let's do this time a different atlas. Let's say or let's do the same. I'm not sure. Let's do this same atlas again. And like this. Oh yeah, since we had a wireframe structure, it remembers what we had last time. So we have it here, and then we go here nodes, and then we go to add nodes, and then we can go here and then say this a park reduce nodes. Yeah, so we can see some of the nodes now, and in the next step we'll try to overlay edges. We go here, add edges, and for this I want to go to the uh, connectivity. Let's visualize the EUDX connectivity here. So now you can see like we have like some nodes here, but it's not looking good. So we just go back to the default settings here, and then and here you see there's like options. So you can just threshold it first. So let's say let me try like 3. So and then see like we have this thresholded still, like there are some nodes are left. So I can just increase the lower threshold to let's say 5, and then now we can see that okay, there's like this brain region. You can see zoom in here. This is the corpus callosum where all the white matter tracks are connecting with each other. And there's like some connectivity which goes like which bypasses the corpus callosum. Like you can see in the frontal cortex, we can see like this connection between these left and right regions, which doesn't really go through corpus callosum. So we can see that there's like two different uh, edges going through corpus callosum, but there's also like this one edge which has like slightly less connectivity strength connecting the left and right frontal cortex. Yeah, so this is you can like overlay the connectivity. And again, let's say if I wanna show you the AL3, which I usually use for my and then we can overlay again the same kind of nodes here, and then nodes uh add nodes and then add edges. I'd say let's yeah, again you can see that okay, this also works really well here. And then again, if you want to if you don't like red and yellow probably you want to see some cool colors, then you can just choose like the blue green, I'd say. And then if I push like the really high, like 6, the lower threshold, then you can see like okay, this is the connectivity for the brain regions. And if you want to see like you can just like try to clip it. If you want to see the lower part of the brain, it's like can do this clipping again like this, and then you can just rotate to see like the central part and the lower part again. So like yeah, so yeah, this is like now we have like cut the brain into like different spheres. um, or let's say yeah, another thing you can do, let's say if you want to just interested in like one kind of connectivity in like one hemisphere, so what are you going to do? So let's say first I'll reduce the threshold here, so let's say 5, so that we get like more edges. And then we go here to the nodes, and then there are options like restricting the nodes. So let's say we are just interested in the left hemisphere. So yeah, so now we have the nodes in the left hemisphere only. Yeah. So now we can say that so we know that corpus callosum connects the left and right, but you can see okay, there's like connectivity between the back of the brain and then the front of the brain. So maybe if there's like some processing which uses the front and the back, then like you can see like this edge going from the back of the brain going to corpus callosum and then again to the front. Yeah, so that was Surf Ice and the DiPy both combined together can give you like amazing visualizations for tractography and as well as for brain connectivity. Yeah, so let me go back to my slide. Yeah, here, and then if we see, so this was corpus callosum, like we just saw it, and this was for deterministic, and then this was for probabilistic. Yeah, so I really hope that you gained something new out of this presentation. And what else we can do after this? So with the connectivity matrix, we can either do like a topological data analysis or right now we just talked about like one patient, or this in the Stanford data set, we had like one sample, but let's say you want to do something more, so you can like gather some healthy and diseased patient and then do that, and then do DTI imaging on them, and then extract the network connectivity, and then try to answer this question at, like for example, it's in Alzheimer's or in some other disease, how does cognitive impairment brain connectivity, or the other way around, if you want to ask like, okay, if you want to perturb some brain connectivity, how does that lead to the cognitive impairment? So that's like some of the downstream questions which can be answered, I'd say, which could be a very interesting thing to explore with this kind of analysis. So yeah, so these are the references. So the first one is like the most cited reference for DiPy, which is like the origin of DiPy. It's kind of cited like I don't know 800 times now, maybe 1,000, and then and some of the other tutorials you'll find it on dipy.org tutorials, and this is my GitHub link for this tutorial. If you follow this, you'll find this all the tutorials like the Jupyter notebooks and all the other analysis, like how do you do connected component analysis, how do you save the tractogram and then load on to Surf Ice. So yeah, thank you very much for your time. Yeah, I'll see you next time. Thank you.